So I got kind of a few different demonstrations here to get hopefully some understanding of what's going on with a derivative, what we're trying to find. So let's start with this one. You guys did that like definition of the derivative last year. Well, no, she called it a difference. You might have how to do it, but that's not what I'm getting at. But that's what this is about. So let's say that we want to find the slope at, because we talked about the derivative as the slope at 1 point. So the slope between 2. So we imagine that there's 2 points that are just so freaking close together that it might as well be 1 point. So let's say we want to find the slope at C. So the slope at C is this dotted line. And the way calculus works, you don't really have to think about it when you're doing the calculus, but it is important to understand what's going on. Right now I'm finding this green darker line. Here, let's do this. This line is the slope between these 2 points. Well, what I really want is the slope at that 1 point. So the way I can do that is to just move this point closer and closer and closer. And you see how those slopes start to become more and more and more similar? And when I get, like, you can't technically get right on top of it because then you don't have a slope between 2 points. But just imagine those 2 points are so close together that you can do that. So let's move it over and do it again. Let's say C was right there, and I want to find the slope at that spot. Obviously this is like too far away. But as I start moving this point closer and closer, you can see it kind of line up, and that's what we're going for, is to find the slope at 2 points that are so close together that they might as well be 1 point. Another way people think about it, this is like the advanced thing we'll get to in a second, is like a surfboard, dude. So if I asked you to draw the surfboard, that's kind of the same, like sketch the tangent line. It's the same idea we talked about the other day, where this was actually discovered because Newton was trying to do something with like the orbit of the Earth around the sun, and just like accidentally figured out what would happen if gravity stopped working. Like, we're going around the sun, everything's fine, and then gravity just shuts off, and you just kind of go off into space. So you're on a curvy road in ice, your tires lose grip, and you're not turning anymore. What path would you continue on? Or if I said draw a surfboard, I'm just trying to like express what a tangent line is. So those are just different ways to think about it. And the derivative tells us the slope of that line. So if I said like estimate the derivative at this spot, I could do it without calculus. I would just estimate the slope of this blue line. Just be like, oh, that looks like it's maybe like up 1 over 2, so maybe a half, something like that. So right now is my derivative positive or negative? Negative, because that line is a negative slope, right? Right now? Wait, not. What now? Nope. Not there yet. What is it now? Approximately. It's pretty darn accurate. So your tangent line will be 0 there. So let's do this. What's my slope now? 0. Positive and getting bigger, or positive and getting smaller? Positive and getting bigger until about there. Now it's positive and getting smaller. That's called a point of inflection. You guys have probably heard that term in like other contexts. And then positive and getting smaller, positive and getting smaller, positive and getting smaller. Back to 0. Negative and getting negativer, which is actually smaller, right? Negativer. The numbers are not getting bigger. The absolute value of the number is getting bigger. So more negative, more negative, more negative. And now less negative, 0. Alright, let's try this last one. This is the, okay. So your y equals x to the third is this blue one. That's the original function. So there's the original function. So let's watch what happens here. My slope right here, very positive, right? Tangent line slope is positive. And getting smaller, so now 0. It's not approximately, I got it to 0, man. And then positive and getting bigger. was true about was my slope ever negative in this scenario? So if I graph the derivative, which is something we're not doing today, but we will soon enough, that red graph is a graph of the derivative. Right. Why does it say zoom out if I can't zoom out? I mean, it's like there's a thing right there that says zoom in, zoom out, move graphics view.
No, go over.
Thanks, Benjamin. So, if I ask you, oh, got it. I see. No, you didn't do anything, man. Okay. So, like right here, your slope is very positive, right? Do you see how the y value of the derivative graph is positive or above the axis? And now my slope is getting less positive, right? What's happening to these y values of my derivative? Less positive. My slope here is 0. What's the value? I mean, it's not 0 perfectly. So what's the value of the derivative at that spot? It's 0. Now my slope is getting more positive, and the y values of the derivative are getting more positive. Okay, why are there two tangents? Oh, that's why. Okay. So right there, my slope is negative, getting less negative, and 0. So what should be true about the y values of my derivative? They are negative. They're getting less negative, then they get to 0. The slope of this graph is positive and getting more positive. The y values of this derivative should be positive and getting more positive. This is a hard concept. I'm not expecting you to fully grasp it right now. We'll practice this a lot. Just trying to introduce. If I can do like sine. Yeah, the derivative of sine is cos. Sine's wiggly, right? So like my derivative over here is 0. And then my derivative in this portion between like there and there is negative, right? So my derivative graph should be above or below the axis during that spot. My derivative graph. Below the axis because this is a negative slope. So we'll see it. See how it's below the axis there? And now my derivative graph should be above the axis. So we're above the axis, then 0, and then below the axis. Sine is, the derivative of sine is cos. The derivative of cos is negative sine. It changes a little bit, but yeah. There's one graph where the derivative and the actual graph are the same. Anybody want to take a guess before I? Well, let's look at those two. Yeah, that's good. Before I do that. Like y equals 3x. What's the slope of that graph? 3. So what should the value of the derivative be at every single spot? There's your derivative. Y equals 3. Or if I have y equals 3, what's the slope of that at every single spot? 0. So what should be the value of the derivative at every single spot? 0. So it should be a horizontal line at 0. There it is. It is 1. I like it. Anyone got a guess? What graph is the derivative of itself? Oh, 0 is 2. So there's 2. So if I have 0, what's the slope of that everywhere is 0. That's good. Yeah, I didn't think of that. You gotta do some calculations. I'll give extra credit for this. But you only have like 30 seconds. Oh, get you got the. If you're looking at your computer, you're not getting extra credit. Y equals infinity. Yeah. Like y equals infinity? Is that the equation we're doing? Let's look at y equals x. What's the slope of y equals x everywhere? 1. So what's the derivative everywhere? 1. I don't know what you mean by infinity. Like, I want a function of x. Like 3x, x squared, not like f of x equals infinity. It would be a horizontal line and your slope would be 0. You know? Should I give more time or is this just getting annoying?
No, actually, this is actually working our brain.
Essentially. No technological resources. This is not it, I'm just showing more. Oh. Who doesn't care? Better care. What? What graph, if I look at the slope of it, has the exact same? What? Equals what? That's 0. No. I appreciate the creativity. You're not getting extra. We haven't used this function in class this year. It's not like some crazy thing you never heard of. I don't know. How many characters are in this classroom? Square root of pi is just a number. Slope is 0. Oh, right. It's a number that's not 0, right? Yeah. I think we're losing focus, I'm going to tell you. Sine pi is the number. Yeah. Probably have to be lowercase. So that is the derivative of itself. The y values of the original graph right here are really small positive numbers, right? Like we're above the axis, but not very much. Well, isn't the slope also a really small positive number? Like it's going up, but like really slowly. And then as these y values get bigger, so does the slope. And it matches up perfectly. So that's the only, besides y equals 0, this is the only one where you can say like y equals e to the x, the derivative is y prime equals e to the x.